The other thing that can dramatically influence reaction rates are the presence of catalysts. You remember that catalysts are special substances that participate in the chemical reaction by lowering the activation energy, but do not show up in the products or the reactants because they're used in the initial step and they're consumed in a later step. One classic example of this is the catalytic decomposition of hydrogen peroxide, which you can see here on this little card, H2O2 decomposing into H2O and O2. The reaction coordinate there showing a exothermic reaction, so the products are certainly favored. But the little dot diagram illustrating kind of the problem, in as much as every one of the reactant bonds must be broken in order to make those products. And so the activation energy of this reaction is pretty high, which means that at room temperature it occurs pretty slowly. And so here in this graduated cylinder we have about 5 milliliters of hydrogen peroxide. And if we sit here and stare at it for a couple of hours, we see no indication that a gas is being formed, that an oxygen gas being formed. The bubbles then indicative of that decomposition. If we waited for a couple of weeks, we could probably slowly see those gas bubbles form and evolve to the top. But the reaction, again, slow at room temperature because of the relatively strong bonds and the high activation energy. We can speed up the reaction dramatically by introducing a catalyst. I'm moving the reaction vessel into a containment vessel in anticipation of exciting things to happen. In this instance, the catalytic component is, believe it or not, simply the iodide ion. And although this is a little bit more complicated graphic here, but it shows you then that the iodide ion participates in a two-step reaction. In step one, a molecule of hydrogen peroxide combines with the iodide ion to make the iodate ion and a molecule of water. And then in the second step of the reaction, another molecule of hydrogen peroxide combines with the intermediate iodide ion to make the oxygen gas, a water molecule, and releases the iodide ion in the products. And since the iodide is a reactant in the first step and a product in the second step, it serves the role of a catalyst. And so as you're watching then that graduated cylinder, I'm just going to add some potassium iodide to it, a small scoop of solid potassium iodide, and we'll see what we will see. Here it goes. And notice that immediately the reaction mixture begins to bubble vigorously, and in fact shoots the reaction mixture out the top of the container. The steam you're seeing an indication of the relatively high temperatures that occur when the reaction rate runs very, very fast. And when we're all done, then water, kind of the only liquid product, the oxygen gas being formed and bubbled out of the reaction mixture. So that if we look at it in a more systematic way here without all the dot diagrams, this shows our catalyzed reaction, where in step one the hydrogen peroxide combines with the iodide ion to make iodite and water. In step two, another hydrogen peroxide molecule combines with the iodite ion to make oxygen, water, and iodide. And if we add up the two steps, we get, of course, the balanced chemical reaction shown there at the bottom. Neither the iodite ion, IO1-, nor the iodide ion, I1-, shows up in the balanced chemical equation because the iodide ion is a reactant in the first step and a product in the second step, and the iodite ion is a reactant in the product in the first step and a reactant in the second step. And so when we add the two reactions, those two components go away. and then shown in the reaction coordinate, the classic catalysis, the original reaction activation energy shown by the dotted line, the new catalyzed lower activation energy shown schematically by the dark line, and the much lower activation energy then explains why we can have a much faster reaction rate at room temperature.